difficult about that. Anyway, so today, very important, it's detailed, it's intense. And I need you to pay attention, okay? I'm going to explain some of the actual processes that we use in clean room. So we started some of this discussion last week, but today we're going to go a little bit more intense, and then actually broader. And I'm going to talk about at least 6 or 7 of the processes. And at the end, I'm going to cover one example, which is going to be a basis for homework number 2. Okay? So, as always, if you have questions, stop and ask me. So what I would like to cover today is mainly a review of the micromachining methods, just like I said. So we're going to talk about oxidation, which we partly did last week. But I'm going to give you the equations and so on, doping, and the various thin film depositions, including metal, sputtering, evaporation. We talked, and some of you had even a question on those. Planarization, what does planarization mean? And then wafer bonding. If you have 2 wafers, how do you put them together? Sometimes you make part of the device on one wafer, part of the other device on the other wafer. Eventually you have to merge them. And how do we do that? So we'll talk about those. So in terms of bonding, of course, silicon to silicon, silicon to glass. Okay, there are various ways of doing this. And then, like I said, I will be reviewing one surface micromachining, one device, which is actually a resonator, which could also be an accelerometer. And we'll do a review of that process. So all the surface micromachining steps, and then there's the homework based off of that. Okay, so the micromachining methods available. So the first one is oxidation. Remember, we started talking about this last week. So it all starts with, so I got some of the dirty silicon wafers that we already have. So it all starts with this guy, okay? And remind me of its thickness.
500 nanometers? Or sorry, micrometers.
Okay, good. Don't forget, 500 micrometer. I'm going to come back to that again and again. Remember, we talked about it. Now, in terms of sizes, what are the available sizes that we have? I mean, one of them is right here. And Danny will tell me, this is a 4-inch. So what's the largest wafer size that we use currently? Sorry. No, industry-wise.
15?
15-inch, yeah. Which is almost 300 millimeters. So 12-inch dominated for some time, then you have 15 inches. Now, it's not easy to make 15-inch of this and have it so planar that the non-planarity is within about nanometers. It has to be so flat, so polished. I mean, you could do it over 2 microns. I mean, 2-inch diameter wafer. But the moment you scale up, maintaining that planarity is very, very difficult. And that's why it took a long time. But anyway, right now, 15-inch. Now, to answer the direct question with 15-inch, possibly you could have about 20,000 devices. One shot. So, in a semiconductor environment, you will have about 10 of these guys with 50,000. So, sometimes up to 1 million devices will be processed at a single time. So, that's called scales of economy. The only thing I like about MBA folks. Because I mean, the prices go down as you scale up the process, right? Okay, so now one of the most important processes that we use on these wafers is oxidation. And you will remind me what oxidation is.
It's adding like a thin layer of silicon oxide.
That's right. And how do I grow? Very good. How do I grow an oxide? Very simple, right? You remember?
Steam.
So you put in a chamber, and that's what you have over here, an oxidation chamber. You have several of these, so we don't process one at a time. So actually you open these chambers, and then you load about 20, 30, 50, depending on how big it is. And you load them inside the chamber, raise the temperature to, now this is important, 850 to 1150 degrees Celsius. That's when silicon oxidizes. Iron, on the other hand, first oxidizes at room temperature, right? I mean, that's why if you put a piece of iron outside, it's going to oxidize, it's going to rust. But you want to rust silicon, you got to raise the temperature. Okay? 850 to 1150 degrees Celsius. Then we have two types of oxidation. One is dry oxidation, where I just use what kind of gas? Anybody? Oxygen. Oxygen. In wet oxidation, however, I use water vapor. Okay? So, how about pressure? So finally, I'm going to have a table where I'm going to summarize each of these processes, and we're going to talk about the main components here, I mean the main conditions, which one is temperature, the other one is pressure. So, in terms of temperature, 850 to 1150, how about pressure? Any guess? Don't guess. You don't know. Huh?
2 bar.
200 bar? So that's what, 1 atmosphere is 1 bar.
Yeah.
So that's extremely high pressure. I mean, do we need to do high pressure? I mean, as long as you raise the temperature, that, that's it. So ambient pressure, 1 atmosphere, which is almost 1 bar, well, 1.01 bar is okay. All right? So 1150 degrees Celsius, 1 atmosphere. Ambient temperature, pressure. Now, remember I said the thickness of the silicon dioxide that you're going to grow is a function of time. Okay? Typically, if you grow 1 micron, these numbers are very, very important. Well, 0.5 micron. In fact, on the table, what I want you to do is, we're going to come back to that. I always improvise on these things. So that's why I don't have it in the summary, but I really want you to put some of these. So, oxidation, typical oxide layer is about 0.5 micron. So with 0.5 micron, you should get insulation. Remember, the reason I want oxidation is for insulation. Okay? So what is the other insulation layer that we talked about last time? Anybody? Remember, that was what material? So silicon dioxide, insulation material. So one is you grow on oxide, the other one is you grow nitride. Very good, silicon nitride. So, but anyway, oxidation, typically we go 0.5 micron. Now the thickness of the silicon dioxide is governed by this equation. So it has to be a function of time, and a time response, and the area, of course. So you have 0.5 times whatever. Do I expect you to remember the equation? Probably it's not that useful to remember, but I want you to know it's related to time and area. Okay? Now, there are 2 things that we need to know. So you take silicon wafer, of course, when you grow it, you're going to grow oxide on top and the bottom, right? So nothing is preventing it. But we're mainly interested on the top one. So that's what you get, half. Now, if the amount of oxygen you're pushing in is not enough, okay, then this kind of process is called reaction limited. Okay? I mean, this will oxidize. If I put it 1150 degrees Celsius, ambient pressure, it will start oxidizing. But to keep on oxidizing, I have to keep on putting oxygen. If I stop putting oxygen, then the reaction stops. So that kind of process, I need you to remember this, is called reaction limited. Okay? Chemistry concept, but extremely important. On the other hand, I'm supplying oxygen, but I'm just letting it hang out. It's not flowing. It's a big chamber. Oxygen is coming in. The rate at which it's going to oxidize is going to depend on how fast I'm making oxygen available to each of the parts. Or how fast am I diffusing it to the layer. So that's called diffusion limited. Okay? So you have 2 types, reaction limited and diffusion limited. Very, not even subtle, very obvious difference between the 2. Okay? All right, so that's your oxidation, and like I said, typical thickness 0.25 micron. Sometimes it's possible we could go to 1 micron, and if you really want to go crazy, you could go to 2 micron. Okay, but that, that's going to complicate your life. Okay, the next one is doping. So remember, so I had my wafer, I took it to the oxidation chamber, I oxidize it, and I have an oxide layer, so this guy is ready. It's insulated. Now I could add stuff to it. Later on I could pattern it, but one of the first things I would like to do is dope it. Now doping, I mean essentially you're putting stuff, dirt, different stuff, okay? dirty in a concept, I mean, that's a concept. Essentially what you're saying is, it's some other material that you're putting in, and that will modify the behavior, okay? So remember, we talked about silicon, and if I want to turn this into N-type, then I have to dope it with, anybody? Phosphorus? Yeah. So for this, you need phosphorus, and if you want to do P-type, you do boron. Okay, very good. So that's doping. Now for doping, again, we have a doping chamber. You take this guy, put in a chamber. This is where mechanical engineers come in. So most of these things are designed. For example, ASML, most of their mechanical engineers are involved in terms of designing their chambers. In fact, even designing the optical systems, the controls and all that kind of stuff, okay? So that's why I really want you to pay attention not only to the process, but also to the equipment, okay? So, in the doping chamber, so essentially what you'll have to do is you'll have to pass gas. Let's see, this gives you a cartoon. So I start with the silicon, I grew on oxide. Now what I would like to do is I would like to dope it in such a way that, for example, I'm interested in N-type, so I'm going to pass phosphorus. Now, I don't want to do that everywhere. And I mentioned this last week. I want to do it only certain locations, okay? So for that, I'm going to do lithography, but I'll explain that later on. Because essentially what I'm going to do is, I'm going to cover areas that need to be protected by this photoresist. But areas where I really want them to be doped with phosphorus, I'm going to keep them open. Okay? So I have an open area, it comes in, you bombard it for, again, how thick you want it is going to be determined by the time. Okay? And I don't have the relationship here, but it's a function of time. Okay? So doping chamber, pass your gas, so phosphorus is going to be in terms of gas. So typically these are high temperature processes. Doping, for example, I haven't given you the temperature, but you're not going to do doping at the room temperature. Phosphorus at room temperature is going to be actually almost like solid, right? Usually you put in water and all that, yes.
With the photo resist,
yeah.
What are you actually having a hole in there? Rather than like the ones that you passed around where it actually has a film that's still there where you can just see through it? Because you need to get the particles down to it, right?
Yeah, I called it a hole, but essentially what's going to happen is you're going to have features, right?
Yeah.
So for example, I have these kind of features. So I want doping to happen in this location.
Okay.
So what I'm going to do is I'm going to cover it with a photoresist, expose it with a mask, which is transparent wherever I have these shapes. Then you pass light, the UV light will polymerize that and it gets depolymerized, it gets washed away. So at the end what's going to happen is everything is covered with the photoresist except that part.
Right.
So that's the opening where I want doping.
But it doesn't actually have like a legitimate opening. It's still it's just clear, right? Like there's still
yeah,
like
it's clear, but of course at the bottom you have silicon.
Yeah, I understand.
So the silicon part is what I want to be doped. So essentially I'm protecting every part I don't want to be doped and then exposing that part. And that's the beauty with the photoresist. Okay? That's the whole idea why I'm doing this patterning. So I'm going to repeat the same thing actually when I'm doing metallization. Because I don't want metal everywhere. I want metal only maybe a certain location. Like a trace here on a bump pad. So again, I'm going to do a lithography, put photoresist everywhere except here, and then I'm going to come and deposit metal. Okay? So this process is going to get repeated, again and again, and finally we'll get a hand of it. And especially when you do, so you'll see actually in your own eyes what's going to look like. Okay, so doping, very easy. High temperature, typically greater than 500 degrees. So it depends, but you could do it greater than 500 degrees Celsius. Boron and phosphorus have to be in a gaseous form. Pressure, ambient pressure. Okay, it does have to be vacuum. Oh yeah, I got the formula here. The temperature is in fact included. So greater than 500, but I think I'm more specific here. So modify the 500 I gave you, okay? 1,000 to 1150 degrees Celsius. I mean, there are processes where I use low temperature, but typically within this range, about 1,000 degrees Celsius, okay? So essentially, you pass gas, like I said. Now, the concentration profile. In doping, really what matters is, for example, when I put N junction and P junction, what you get is a profile. You don't get a very sharp. I mean, when we draw it, we draw a cartoon, which is rectangular, but typically what you get is a profile like that. Now, because at the top, you're going to get this part diffused and, doped. When the other part comes in, it's already covered. So what it does is it starts building from the bottom. Now, at the end, you're going to be limited how much you could go. Okay? The longer you keep it. Remember, everything else is covered. I just have that opening. As I'm pushing it, it doesn't happen to that, it's going to go straight. It's going to follow this kind of profile. And that profile is given by this equation. Again, it's a function of and then the concentration. The concentration of the dopant. So if my concentration of phosphorus is low, then of course the amount of phosphorus doping that you're going to get is limited. Okay, so at this point, we have oxidation, we have doping. Okay, 2 out of 8. Yeah, so the profile is related to the thickness, right? No, yeah, there you go, the junction depth. You see this guy? This curve? Yeah. So that gives you the time, and that gives you, so the profile means, this profile is that depth profile. Okay? And because the depth over here and over here, so, well, you can find the depth, but how far it's going to be away. So that's what I would like to determine. So you get a curve like this, actually inverted. Okay? All right. So, step number. Yes.
What are the units on the concentration?
Beg pardon?
What are the units on this concentration profile?
Picogram per microliter per volume and so on.
Okay.
So, no, are you talking about the dopant itself?
I was just wondering, how do you quantify this concentration profile? Is it just dopant per volume of the...
Oh, yeah. Right. So, for example, to have an efficient N-type activity, to have excess of electrons, you could have N number, 10 to the power N number of electrons excess, or 10 to the power 2N. That's going to depend on the concentration that you want. Okay? So these are all, again, dependent on the functionality of the end, what you want. But typical numbers are available. I don't remember off the top of my head, but anyway, it's enough to give you 10 to the power of N number of electrons. And N is not a small number, okay? N is greater than 9. Okay, the third set of processes are extremely important. So, we insulated it, and if I wanted to create a diode or a switch, then I did my doping. But more importantly, I need to add some interesting layers. That's where the interesting stuff happens. So for example, if you're designing a sensor, you have to deposit some interesting stuff to it. If you are putting a conductive layer, you have to have a metal to it. So for that we use what's called CVD. Well, there are a number of them, but in general they are called thin film deposition. Okay? Now let's agree on one term. When you hear the word thin film, by the way, there are books just written with the title thin film. Okay, it's a whole discipline by itself. Let's get a few to the numbers. So when you hear the word thin film, what do you think is it? What? Nanometer, yeah, not bad. Yeah, maximum would be, so that's the, well, thin film on the lowest is an angstrom, which is, how many angstroms make 1 nanometer? Anybody? Okay, very good. Yeah, very good. So 10 angstroms make 1 nanometer. So thin films start from angstroms, okay? Sucks, I don't have enough space, but so when we say thin film, several angstroms, okay, tens of angstroms, to what would be the maximum thickness, Omar, if you have to guess? Tens. Right, 10 angstrom, 20 angstrom, 30 angstrom, 40 angstrom. Yeah. Tens of angstrom to maximum.
100 micrometer.
Oh, good. It's right there, right? You got my first law. Yeah, that's right. A few nanometers. In fact, I mean, few nanometers, angstroms, all the way to 100 micrometers. Yeah, I'm glad I put 100 micrometers. Now, of course, there are people, very few people do 100 microns, okay? This is my interpretation, okay? If you go and interview with a very typical semiconductor company and there is 100 micron, they don't want to give you a job, tell them to talk to me. So typical semiconductor, because remember I told you, like metal, all that much gold, I mean, you're not going to put 100 micron. So typically we put only 10 nanometer, 20 nanometers, and so on. But now we're using more and more polymers. And remember, in San Diego State, our distinguishing feature in terms of microfabrication is we marry silicon with carbon. A very unusual marriage, but it works. So when you put polymers, then you go to all the way to 100 nanometers, micrometers. So I really want you to remember this, okay? So that's your thin film. Now, what are the processes available for thin films? The first one is CVD, chemical vapor deposition. As the name implies, it's going to be chemical, it's going to be positive. But in what form? In vapor form. Therefore, it's high temperature process, by definition, right? So, well, what do we do? For example, these guys, this is an industry scale from a company called Lesker. These are huge CVD systems, but we also have a CVD system in our clean room. It's this size, probably what? 18, 20, well, about 36 inches tall. So what you do is, again, take your wafer, already stuff is on it. Remember, in the semiconductor industry, we said you can do up to 25 to 35 layers. The MEMS about 8, 9 layers, so you're doing step by step. So far, you've done 2 or 3 layers. Now, you want to do a deposition of material. For example, platinum, gold, aluminum, silver, you know what have you. Okay, or some adhesion layer first. So what you do is you take these guys, you load them into a chamber, either this chamber or that chamber. You don't do one at a time. In a lab, yes, one. In an industrial scale, you know, hundreds and hundreds of these wafers. You load them. And, for example, if I want to do it, this is very important, and it's going to form the basis of next week's lecture. Therefore, I need to put the name here. Poly CSI, also known as poly silicon. Have you guys heard of dirty silicon? Silicon, you guys have heard. So that's all clean so far. I mean, this is the layman's interpretation here. Some of the newer solar cells. Next time you see a solar cell on a lamp, street lamp, pay attention. It doesn't look that clean in terms of crystalline structure. Homework number 1. Homework number 1, what I asked you to do, these are very, very clean crystalline structures. So the expensive silicon is single crystalline. Okay? So that one is very, very clean because of scale of economies. I remember about 6 years ago, you could buy those solar panels for about $900 or $1,000, but now the price has gone down to about $200 because of scales of economy and so on. But still, that's not useful because of 2 things. It's not useful always because of 2 things. One is, if I want to create or fabricate a silicon layer as a structural material, I want to build a beam, or I want to build some kind of membrane. So I need a form of silicon, because remember, we talked about the material property, Young's modulus. Somebody surprised me. What kind of number are we talking about with silicon? Young's modulus. Homework number 1. Very good. 130 to 190 GPA, and that was your homework, if you remember, partly. So 100 is 130 GPA, 111 gives you 160. I love this number, I'm going to come back to it again and again. 190 is for 111, right? Now, that's very impressive. That's a very excellent structural material. But I cannot deposit single crystalline silicon. So what we do is we have a form of silicon called polysilicon. You start with silicon nitride, you heat it, decomposes, the nitrogen is taken away, you can combine it with other gases, it reacts. But the silicon that forms as you're decomposing silicon nitride, it's not crystalline, I want you to pay attention, it's poly-C. And poly-C is an amorphous structure which really looks like actually snowflakes. And I'm going to show some of the pictures. I did show you some of the pictures last time. So that material actually deposits, and you could control the thickness or whatever. At the end, you're going to have a silicon material, except it's not crystalline. Now, the beauty with that is, and I want you to remember this number, you're going to get a material with Young's modulus of 160 gigapascal, which is the same as actually 110. Okay, that's impressive. So now, how do I do polysilicon? So what I do is I use CVD, which I briefly mentioned. So you take this guy, put it in a chamber, pass in silicon nitride, again high temperature. Now I ask you for a temperature. Let me give you a hint. Usually 1,000 degrees Celsius is safe. You could go with 1,400, 1,500, but nothing more than that. I mean, 1,400 degrees Celsius, folks. It's not easy. It's a high temperature. It's a very expensive process. So nobody wants to go more than 400 degrees Celsius. Okay? So keep that in mind. Somebody asks you about a material you've never heard of, and they say, okay, look, I'm doing a deposition. What kind of temperature, high temperature do you think I have? Never say 3,000 degrees Celsius. Okay? Because it's just incredible. I mean, you cannot have 3,000 degrees Celsius. So 1,000, 1,200, we could have that kind of temperature. Okay? So 1,200 degrees Celsius, silicon nitride. The nitride decomposes, you have silicon. Silicon falls on this in a nice way. Now, remember, and this is going to be a basis of my next lecture next week or the week after. There's a process called MEMS. I'll be very happy if you remember it next time we meet. It is so important that it has a whole lecture just dedicated to that. Okay? So again, the way that happens, I do another layer of photoresist. And I pattern that. And I make openings. Wherever I want polysilicon to be deposited, I make openings. And then I put it in that chamber, then polysilicon will nicely deposit on, I mean, it's going to deposit on everything. But remember, the photoresist, I can wash it away, right? It's a temporary material, so it gets washed away, but the remaining part is whatever you add for. Okay? So that is called CVD. Chemical vapor deposition. It's the most important integral part of any semiconductor process and any MEMS process. Questions before I talk about the varieties of yes or no?
So the glassy carbon that you're working on your lab research,
yeah.
You do the deposition through chemical vapor deposition or which?
Well, it's a little bit different.
Okay.
But I'm going to mention something, so hold on to that thought. Any questions? I want you guys to think. I know it's Friday, but look, the only way we're going to survive this class is any questions? No? Okay. So, it turns out we don't want to do the high temperature always, okay, the 1,000, 1,200 degrees Celsius, not for every material. So there are certain materials where actually you could do a low pressure. Again, with CVD, by the way, it's typically 1 atmosphere. We're not going to pressurize things, okay? Again, as a piece of knowledge, just like the way I told you about the temperature, right? Never more than 1,200 degrees Celsius or 1,500 degrees Celsius, okay? Pressure typically in these processes, either you have atmospheric pressure, okay, 118, because you don't want to pressurize. Pressurizing is expensive. But you could do vacuum. Vacuum is also expensive. But vacuum makes things interesting. So, when I ask you about pressure for a condition, I want you to realize it's either 1 atmosphere, or it's partial vacuum, or it's total vacuum. If it's total vacuum, of course, you can't put stuff. If you're putting stuff, then it has to be partial vacuum. Okay? So think process. I mean, there's some sense to how these things are done. Okay, now, what people have discovered is they could use low pressure, a little bit of vacuum, 10 to the power of minus 1 torricelli. Of course. Then the film quality tends to be very good. Now, is film quality important? Of course. If you want to know how was my day yesterday, it was bad. Because our film sucked. We had a metal deposition, and then we scratched it, and it was just flying away. So I have to meet an old student who graduated from my lab, is working somewhere, and I'm talking to him, how do we solve this? But anyway, the point is, if you're making a living in this area, yes, film thickness really matters. Okay, so you want the film to stay. You don't want it to be scratched. You want it to be stay for a very long time. Now, it turns out you could get a very, very good film quality if you could do partial vacuum. But the partial vacuum we're talking about is 10 to the power minus 1. That's not a big deal. Okay, so that's called LP, CVD, low pressure, chemical deposition. Okay. All right. Then. Oh, what's number 3? Oh yeah. Well, it's number 5. Okay. Yeah. I don't know why I changed it, but let me see if you guys are open to tweaking, live tweaking. All right. So we talked about CVD, then we talked about LPCVD, right? So the most natural thing was actually going for PCVD. Okay. So map number 5 to number 3. Okay. PCVD is plasma enhanced CVD, and I'll show you. We have this equipment in our lab. So this guy is our CVD chamber. At that end, I have an RF unit, and I can push in gas, 4 gases: nitrogen, argon, methane if you want, or whatever. Okay. Now, if I put an RF power to these gases, actually what you create at high temperature, you take a gas, high temperature, high energy, what do you think happens to the gas? Plasma. There are atomics, right? I don't know if you have noticed, 5 and 8 or 5 per second, General Atomics has been working on one project, fusion, nuclear fusion. Before you guys were born, before I was born, still around. But essentially what they're doing is that they create plasma. So if it works out, it's going to be very cheap power source and all that. But we know you take gas, high temperature or high energy. Okay, you're energizing it. So at the molecular level, actually, you're creating high temperature at the minute level. The overall temperature may not be that high. So that creates plasma. So I could take my chemical and turn it into a plasma, and it deposits much nicer. Okay, I could get a very good film. So that's called PECVD, and we could do it in our lab.
Is the plasma just sort of like random, or do they find magnetic field is sort of?
No, well, you have magnetic field if you want to play with it, right? You want to contain it and all that. So that's the general atomic field.
Okay.
But in our case, in the semiconductor thing, what we want to do is we have a gas, but I want to heat it so fast, but not heating the whole thing, but by consuming so much energy on this. So essentially what I'm doing with this guy is, for example, when I'm doing CVD, I'm raising it 1200 degrees Celsius, so I have 50 amps of current coming in, okay? And then this is a heating chamber. So 6 hours it takes me to reach that temperature. Oh, well, not 6 hours, about 3 hours to reach that kind of temperature. Okay, so it's expensive. From the energy point of view, it's expensive. So what you do is, you use RF power. Again, 50 amps, concentrated. You do it on RF power, that energizes the gas, and you create plasma. In the plasma, I mean, again, high temperature, but it deposits fine. Now, there's a material called graphene. That comes to that. So for the glassy carbon that we do, we don't use plasma enhancement and all that kind of stuff. But if you want to create graphene, which is supposed to be an awesome material, I mean, you could look it up. With graphene, then you have to use PCVD. Okay, so CVD, LPCVD, low pressure CVD, PECVD, plasma enhanced CVD. Okay. Now let's go back to the other ones. Any questions so far? All right. So oxidation, we already talked about that, so you can read. The other one is, so before I joined here in San Diego State, I was working in one startup company, my last startup company. Now, I was not the founder, I just joined a startup company. So this company actually had a lot of opportunity and huge momentum and all kind of stuff around them. What they were doing was, they make this small feature, just like the way we're doing with by CVD and all that kind of stuff, and patterning. They took the same concept and they made it to a concept that existed way, hundreds of years ago. Have you guys heard of this gold-plated watches? Essentially what they do is, they take the watches, put them in a gold-carrying solution, and then you apply voltage. And out of the cathode, so it's called electroplating. So gold is Au plus, then it goes to the anode, okay, the negatively charged location. So that's a very old technology. I'm here to do silver plating, the gold plating, and all that kind of stuff. Now they took that thing and then they said, okay, if we pattern, use sacrificial layers and all that kind of stuff. So one of you will be doing maybe a project on that area. So it's a little bit different from what we're discussing. So that's why I'm not going in detail. But what I want you to know is, through electrode deposition and electroplating, you could make very interesting smaller devices. Just one more piece of information. Have you guys heard of arming and saving? Arming and saving. Arming is you arm it, save is, it's not a word that means the military thing. If you want to save, you call it save. The nuclear box. So every countries with a nuclear bomb, they have this box where the combination keys are. Then you send that, and then at every level. So remember, some of these industries, so you have to have a safety kind of level, right? So what happens is, if you want to fire any of these high-impact devices, okay, particularly nuclear devices, so the arming technology has to have 3 or 4 levels. Because you don't want some crazy guy, drunk guy, just doing only one shot, and then one procedure fires. You don't do that. I mean, as an engineer, if I give you a task, you will create 5 levels. 1 and 2 has to happen before something happens, and then 3 has to happen, right? So for that, what's called, so there's a procedure for arming and saving. So these are mechanical devices. So you have to engage number 1, and then somebody has to approve. Then if that's engaged, then the number 2 could get engaged. So there are about 5 to 7 levels. Now, it turns out, and I used to work in this company up in Los Angeles. The military was interested, so their technology was way back from the 1950s. And they had these mechanical devices for arming, because there was no micro-electrical device at that point. So what they wanted to do was come up with mechanical devices, MEMS devices, which are actually controlled mechanically and electrically. So we were doing, so this is not the saving and arming, I mean, you can't show that. So this is just a gear. So the point is, so the old electroplating and electrodeposition method is married into patterning, sacrificial layer that we talked about in MEMS, and you could have these kind of devices. Okay, so typically they're made of nickel, which has very compatible Young's modulus. Okay. All right, so we covered pretty much everything. Yeah. Then the last one is epitaxial silicon. So essentially, if you want to grow one layer of silicon crystal, epitaxial, but we're not going to worry about that too much.
I'm just kind of curious, what kind of voltage do they usually use for electroplating?
High voltage, actually. So the typical watch and stuff, it's about 5 volt, 10 volts, you can do that. But if you want to scale, so the company I told you about, that's still startup company for 30 years. The biggest problem is we want to scale it out. Voltage scales up and all that kind of stuff. But anything from 5 to 60, 70 volts. Yeah. Any question? Okay. All right, now, remember the story. We started with this guy, we did oxidation layer, insulation layer, and then we deposited metal. We also did CVD, doping, because we wanted P-type, N-type, because we wanted switches and so on. But we kept on mentioning, I erased it, that patterning. Remember, I don't want metal to be deposited or CVD everywhere. I don't want boron to be doping everywhere. I want only certain locations. So what I do is I have to do what we discussed last week, which is lithography. The whole lithography process. So, stuff like this. So I want my metals only in certain locations. Okay? So what I do is, remember, I start with this, and I want you to pay attention. And I deposit photoresist. And we said there are two types of photoresist. Does anybody remember? Well?
Negative photoresist and positive photoresist.
Excellent. Negative photoresist PR and positive PR. And I gave you towards the end, when everybody was just trying to rush out of the building and then start the weekend, I mentioned some commercial products. Does anybody remember the positive resist that I talked about? Why I'm doing? Yeah, good. Yeah. Okay. Excellent. And you'll be doing this in a couple of weeks in the lab, so should be. How about negative resist? They said, oh, nice. Okay. So you guys take notes. All right. Okay, I like this class. Okay, SUA. Shipley, SUA. So, now depending on what you want to do. Okay, so let's say typically we want to do positive photoresist. Then I take my wafer, so remember you have your substrate, and you did the other things. When I say thin film here, this your CVD, your doping, all that kind of stuff has happened over here. Then on top of that, I want to add one more layer. So every time you want to add a layer, it's not just going to be complete layer, because you want to have a patterned layer. That's the whole essence. So what you do is you put a photoresist. So let's assume we're doing a Shipley resist. So you take it to a spin coater. So it's a small polymer material. Take it, pipette it out, put it on top of this, and spin it. So depending on the RPM and how long you keep it, then you will have a variety of thickness. So the more the RPM, the thinner it is. Okay? The lower the RPM, of course, the thicker it is. Okay? At the end, what you're going to have is you'll be surprised, a very, very nice, planar, thin film of photoresist. Now remember, photoresist is sacrificial layer. We don't need it. We want to get rid of it, but it has a mission. So what's its mission? So I put my photoresist, then I bring my mask, and I expose it to a UV light. So that's our UV light source. Yeah. So you apply a UV light. Then the transparent one, so this material is sensitive to UV light. That's what I told you last week. Now, with a positive photoresist, what happens is you hit it with a UV light, depolymerizes. It becomes weaker. Okay, the crosslinks are broken. Then, once that happens, you take it to what we call a developer. It's a chemical, which just washes away the depolymerized part. So once that's taken out, then what happens is, remember, the black one. So the white one, the transparent one, UV light came in, depolymerized it, therefore I expect this guy to go away. And that's what happened. The black one, however, no UV light, it's not attacked, it will survive, then you're going to have these two. Now, this is where the mission is. Whatever I want to do, I can do at this point. Because this guy opened it for me. It opened this thin film for any kind of operation. Okay? But this guy over here and over here, it's protected. Nothing is going to happen. I mean, you're going to deposit metal and all that later on this, but once I put in a chemical called stripper, then what's going to happen is it's going to strip it away. It's going to wash it away. Okay? Because it's a sacrificial material. Its mission is over. It's gone. Then at that point, what you're going to have is whatever material that you want is going to be here, here, and there. So the whole process of putting a photoresist and then exposing it to a UV light and developing it and then eventually stripping it away is called one litho process. Litho stands for lithography. Are you guys with me? I've been trying to build this story the whole 4 or 5 weeks. Because remember, day one we talk about, yeah, how do you perform this? Yeah, you use a transport photolithography. But this is where it becomes clear. Everybody with me on this? Okay. So why?
In terms of the application, when do you want it to be polymerized and when do you want it to be
Okay, that's a very good question. Now, so typically, what people use is a positive photoresist, okay? For most actions. It's cheaper. And it's very easy to work with, easy to wash. Now, you will know this when you go to the cleaner. Because if you touch the negative photoresist, it's going to stick to your, if you're not dressed properly and all that, it sticks to fingers and all that, sticks to equipment. Some labs don't like it. In fact, they banned it. I remember I talked to one guy who was running a facility. He said, "Oh, I don't like SUA. It just messes up my life. I think it's lazy." In our lab, we know what to do with that. So, however, there is another thing called, I don't know, some of you may have taken this. So, those of you who are interested, so the minimum expectations I want you to know is SUA and Shipley. But there is another material, photoresist called Future X. When you come to the nano fab, your trainers are going to mention this. Okay? It's called Future X. So that's a negative resist. So every time you want to do metal, this is what typically we use. And almost all labs have that. And there is a reason. I'll explain that down the line. Okay? Yes? But I'll give you a chance. Yeah.
Why would you want to use like a negative photoresist over a positive photoresist? You know,
well, I'll give you one example. Okay. So remember, the whole idea of using a photoresist is a sacrificial layer, right? Protected. But it turns out some of these negative photoresists, they're polymers. You pattern them. After that, you just don't want to wash them away. You take them and you put them in a chamber, heating chamber. They turn into this amazing material called carbon. Remember, a polymer is hydrocarbon, C. O. What else? H. So you have carbon, you have oxygen, you have hydrogen. Put them in a chamber, heat it, oxygen and hydrogen will go away. You're left with carbon. And it turns out that carbon is amazing. So in my lab, what we do is that particular carbon we're interested in, then graphene also, same way. So for the newer materials, especially the carbon materials, negative resistance. That's reason number one. There's reason number two, we'll talk some other time. Yes?
you explained about photoresist. Does negative photoresist harden when exposed to UV?
Yes, it's the opposite. Very good. In fact, I was going to forget mentioning that now. Positive photoresist, the key word is this part which is transparent, the polymer actually gets depolymerized, which means the crosslinks are broken. It becomes weaker. In the positive ones, the negative ones, the transparent ones actually you apply light, they polymerize, they cross-link. It's the property of the polymer, and that's a distinction. So because it becomes stronger, then you wash away the non-strong one and the stronger one. Yes?
Then would you expose negative photoresist to light before you bake it?
With positive photoresist, yeah.
Can you bake it immediately?
First you want to pattern, right? Because in patterning, remember, the whole idea is I want features, right? At the end, I just don't want just a layer. I want a device which looks like something. Maybe it's an electrode, so it has a sharp end. Maybe it's a surface electrode or a penetrating electrode, whatever it is. So first, you have to do the patterning, and this is the patterning, right? Once it's patterned, it's ready. It's a polymer, so you bake it. How you baking it? Actually, you burn it. But very good questions. I like this question. So when we do the design project part, I think we're going to have some of you work in some of this aspect. Okay? Yes, Will.
When you move on to apply another layer, using photolithography, how do you prevent the photoresist from filling in?
Well, okay, very good. So what you do is, remember, in the context I'm describing right now, photoresist, their job is being a sacrificial layer, right? Allowing me to do stuff by patterning. So, once you have deposited the other material, let's assume, some kind of metal, and by protecting this, then at this point what I'm going to do is, look at this, what happened. I wash away the top part. So what am I left with? The green guy. But the green one, I also do something, patterning, right? So the photoresist, before I remove it, I'm going to do some kind of etching, which I'm going to cut. I'm going to explain that part. So what happens is you etch. So this guy kind of acts like protection. Then once I make the opening, I can deposit or I could etch away stuff. In fact, the way I should have explained it, let me give it one more shot. So the way I explained it, I said, okay, we pattern in such a way that this allows me to do a deposition, right? Selective deposition. Okay, that's number one. The other one is actually that allows me to also do a selective removal. Now, in this particular case, in this cartoon, what I've done is, this guy's protected, I come in, and I'm going to etch away this part, but that guy is protected. And then once this is washed away, I have only this guy left, so I wash that part. At the end, what do I have? I have the green part, selectively etched. Does that make sense? So at this point, the photoresist is removed. I'm ready for the next layer. So then you start another series of lithography. Make sense?
Yeah, my question is really like, imagine, so say you're trying to do that exact same pattern, but scattered over just the same distance. Then when you go...
Yeah, you mean the same plane?
Well, say just that simple pattern up there on the board.
Yeah.
Say you're trying to do that, but scattered over one little rectangle thing.
You mean one on top of the other?
Yeah, exactly.
So you have to repeat this again and again. So like I said, you have to do one complete litho process, which is deposit the photoresist, put your mask, expose it, do your thing. Then after you've done either addition or subtraction, then remove it. That's one litho process.
Yeah.
You want to do the next layer, redo the whole. So that's why this is for patient people. Does that answer your question? So we do it series by series. But it turns out, usually what you want to do is you don't want to repeat the same layer again and again. You want to do one type of shape at one layer, second layer a different shape. Right. So some of this will become more clear inside the people for you in about a week.
So in this case, the photoresist acts just like scaffolding does.
Yeah. That's what we're looking at. Yeah. Scaffolding, it allows you to selectively deposit or selectively etch. So I'm going to introduce this concept more in 2 weeks from now. So this actually action is called masking. Now, this is where it becomes confusion. I mean, very confusing. I call this mask. But I also call the action of protecting my layer masking. Okay, so we like messing things up. Okay? So when I say masking, so please keep that in mind. It messed me up a little bit at the beginning. We run out of words, but anyway, so you need to keep this in mind, but I'll try to explain this again and again. Now, so at this point, we know positive lithography, we know negative lithography, and one more important thing, which I briefly mentioned. Remember, CVD and all that we talked about was actually adding a layer. But what if I want to remove stuff? So that's done through what we call etching. Okay? So we have two types of etching. So again, etching is done in the same thing, again in the chamber, but you have two types of etching. One is dry etching. The other one is wet etching. And as the name implies, if it's dry etching, you're going to use gas. Very corrosive gases. Okay? Wet etching, essentially you take it and immerse it in a liquid environment. Again, remember that lithography process that we did. We did our thing and then we kept the photoresist when it was protecting some areas from being attacked. And here's where it becomes interesting. Polymers, they look weak and stuff, but they're good. There are some acids which will eat metal for breakfast, but they don't attack polymers fast. And that's what happens actually over here. So all the etchants that I'm going to use, I want to etch silicon, I want to etch metal. They will etch the metal. You can see it, in fact, in front of your eyes. But the polymer stays. Of course, if you keep it long enough, it's going to be etched. Okay? Now, wet etching, like I said, involves a chemical. So you have your wafer. It's protected by your photoresist polymer. That's why I was telling you about this story. I put this in a chemical, and then whatever part I don't want gets etched. For example, if it's a silicon, and I'm covering it with photoresist, places where I don't want to be touched, but wherever I want it to be touched, there is an opening. I want the silicon to be etched. What's the etchant that I'm going to use? I've mentioned it since day one. KOH. Take that, put in KOH, just in a buffer. Now you'll be surprised, the kind of buffer that we use, just like that lunchbox, plastic. Because the acids and the bases don't attack plastic. So you put it there, then it waits for an hour, half an hour, whatever, it etches away the silicon. So that's called wet etching. Dry etching, so with wet etching with silicon, what's the angle that we get? Round button. 54.6. So with wet etching of silicon because of the crystalline structure, so typically in wet etching you get, if it's crystalline structure, you get this. Now, last week I did not finish the discussion. There are 2 or 3 slides I wanted you to go over by yourself. If it's isotropic material, like glass, the way it's going to etch it, and I'm going to ask you this in the exam or whatever, so you have to read that PowerPoint. So in glass, the way it's going to etch it is because it's isotropic, some kind of a spherical form, without any, in all directions, as opposed to crystalline structure, which is going to be along the planes. Okay, so remember that. Now, dry etching, however, you're going to use a gas. It etches in a very straight manner, whether it's crystalline structure, non-crystalline structure, isotropic material, non-isotropic material. It's going to etch them straight. Okay? Now, I want you to remember something whenever I mention dry etching. the most common dry etching gas is called HF. In fact, if I had a red marker, I'll use font size 155. What did we talk about HF? Be afraid.
Because you can't.
Feel it.
Very, very afraid. Yeah.
That's the worst part, you can't feel it, so you can eat right there.
Yeah. Of course, because of that, I mean, look, I'm here, I'm hanging out here, I'm relaxed, I'm not worried about my students, losing their finger, body parts and all that kind of stuff. So we don't use that. Now, the very large facilities use HF, extremely controlled, but you pay a price for that because it's extremely controlled. Typically, that goes by airflow. Nobody wants to lose that. I mean, unless you run, particularly a university setting, okay? Intel has a large fab in Arizona, Chandler, Arizona. I mean, they run it in shifts, 3-4 shifts. So always you have the clean room manager, safety manager, and all that kind of stuff. So yeah, it's okay. But in a university environment, our lab is the only one which runs 24 hours, from what I know. I know UCSD people, UCI, Caltech, UCLA. They all close out airflow because of, they're afraid of chemicals like this, not only HF, but other chemicals. Now, we don't use HF by itself, we use another thing called BHF, where B stands for be afraid. No, B stands for buffer. So don't forget that. So B is buffered. So essentially it weakens it, but again, I'm not trying to scare you, but when you do this kind of stuff, in fact, scaring is good because it's a job security. They wouldn't have to take your job. There are some professors who come to the clean room and they run away. And I think, oh, these ignorant guys. But anyway, BHF, it's buffered, it's less corrosive, it's in a liquid environment, okay? It's not gas, okay? But it does the majority of stuff that I wanted to do, the same way as HF. So that's what I want you to remember in terms of etching. Any questions? So I mentioned about anisotropic and isotropic etching. I want you to read this by yourself. If you have a crystalline structure, it's going to etch it along the crystalline plane. Homework number 1. Okay. If you have glass, which is isotropic, the same property in all directions, then it's going to etch it in every direction, and at the end you're going to get this boring figure. Okay? Just like a ditch. So the other one is read. I mean, that's all I need you to know at this point. Then what do you think remaining is wafer bonding? But before that, any questions?
I'm actually kind of curious, because I know we use that electroplating layers, but do we ever use it in reverse and actually sacrifice it? Like, say, if I had a polymer on top and I put the current in reverse and I actually just
Away that there.
Do they have a process like that?
Yeah, I guess you could do that, but remember, you have to isolate everything else and put the anode and put the cathode. It becomes a little bit more complicated, so much easier to use polymer. Yes. Hold on, folks. Hold on. Yes. HF. HF for dry etching. Yes. Yes. Yeah. So because we get so much scared about HF in the gas environment, so the B makes it buffered. So you put in some kind of base solution.
That would be the wet etching. No, yeah.
No, it's a wet etching. Yeah. Again, the story I forgot to tell you, that the reason that you don't want HF is, first of all, it's gas. It's all over.
Yeah.
It's all over your facility. You can't control it if some valve is not working. In fact, when you go to the clean room, I mean, I was involved in the design of EIS building. When it was designed, because we had to design some of the piping. So we have 4 types of pipes. I mean, ducting, so some of them are just for HF. Even though I'm not planning to use HF, I had one installed for HF because you don't want to mix stuff. So all this is regulated, okay? And then, but anyway, so the problem with that is, if it's a gas, if there is any problem with the plumbing, there is or valving, then it just thin air, and you don't even feel it. All you see is just people coming with, lesser parts than they were in. We don't want that. So what we do is put in a liquid form. It's buffered. I know what it is. I can control that, and it's less dangerous. Right? Anybody?
I was just going to give a clean room procedure. Does it ever get to the point, say if there's a leak, they'll lock you in that clean room?
Oh yeah. We have that procedure. So when you guys take training, so the first thing is we're going to give you about a 600-page document, but we have the shorter version. It's 595. Oh. I know we have a procedure. Some of will run about 30 pages. We'll take up that. Okay, now I would like to cover the last topic in the first part, and then that will give me about 20 minutes to cover the next part. So it turns out, sometimes it's useful when you do your design project, you're going to appreciate this. So sometimes it's very difficult to build things one on top of the other. You don't have access. So what you do is, you build the stuff on this wafer, the remaining parts on another wafer, and then eventually you want to bond them. So that's called wafer bonding. Okay, so what I'm going to show you is the two types of bonding. So essentially you can create all type of 3D structures. Now it turns out, well, let me see if I have the two physics. So one is hydrogen bonding. Yeah. So in hydrogen bonding, or fusion bonding, let me see. Yeah, one is anodic bonding and the other one is fusion bonding. Yeah, okay. So what you do is you take these two wafers. Of course, you have to clean and all that kind of stuff. Then you contact them. You have to align. Now that's where it becomes really weird, because at the back, just nothing is polished. You can't even see what's in the inside. So there are tricks to put some alignment mark on this guy and alignment mark on that guy. And when you go to the clean room, you'll see our exposure system has an alignment mark. So the optics is in such a way that it sees both ways. So you come in, you align them, and you put them together. So you're hoping that materials on the top really are aligned. Remember, we're talking some of the features are 10 micron. So you're aligned by 15 micron, everything washes away. And it happens. 10 micron, 15 micron, you're misaligned by 5 micron, you get a weird structure. So it's sensitive, but you get trained to do that. Now, once you've done that, essentially what you do is you take this guy, I can put it in a heating chamber, 1100 degrees Celsius, nothing else. You'll be surprised, they will bond. So that's called hydrogen fusion bonding, okay? So essentially what happens is you have hydrogen bonds forming. So it's a covalent bond. So chemically they're bonding as you're heating. So it creates hydroxyl group, carboxyl if you want to do the chemistry. Then the seal between the wafers is as strong as the silicon crystal itself. So that's one type of bonding. Luckily you have only two types. So fusion is the first one. They fuse together. The second one is anodic bonding, Omar.
When you put them together and put it in the chamber and raise the temperature,
yeah,
the raise of temperature, it doesn't affect the layers that you.
Very good question. Yeah. So in semiconductor, so some of the layers could be sensitive. They don't want to reach 1100 degrees Celsius. So for that, you're kind of screwed. You can't use that. So then you go to anodic bonding. In anodic bonding, usually it's silicon with glass. In fact, I didn't bring my glass substrates. You could get this in quartz, glass, what have you. So, particularly for biological and chemical application, okay? So you don't need the top. So you need a cover. So you're passing blood and liquid and all that kind of stuff, and you want to be able to see things, cells and moving and all that. So what you need is, so you have the structure created on a silicon, and on top, all you want to do is put a glass. So the way that happens, you have a silicon, put your glass cover, apply voltage. You need a voltage, 5 volts, 20 volts, max. Again, temperature, 400 degrees Celsius. You don't need 400 Celsius. 200 may do it, okay, over an extended period of time. Then you'll be surprised. Glass actually bonds with silicon. So that's how typically microfluidic kind of biosensing kind of device are. Any questions? Okay, so I don't know if you realized it, but what we've done last week and this week is cover the major lithographic processes. So at this point, you're ready to understand a very well-known process called MEMS, which we're going to cover next. Well, I'm traveling next week, so the week after. Okay. Now, before that, I'm going to take 15. So I'll summarize this, and then I'll cover one complete process. So this is a summary of whatever we've been talking so far. Okay, and the majority of the stuff is already here. One thing I started and did not finish is in terms of thickness. So if you want, you could take, now I love this chart, and I'm going to ask you an exam. Okay, there's no question about this. Now, if you are, I've seen people taking this and, or have I seen? No. In fact, in my mind I was thinking they will modify it. But I always advise my students, take this as a guidance, and you know, I mean, it's editable, it's not a PDF, it's a PowerPoint. Take this table, add additional stuff to it, okay? Then you will know about the process. So when you go to clean room and all that, you know, becomes easier to know what, you know, the capability of each of these processes. Now, oxidation, remember I told you 850 to 1150 degrees Celsius. Temperature, pressure, typically all of them are ambient atmospheric pressure, except, as the name implies, LPCVD. Graphene, some of the process like graphene and the metal deposition, actually, where is metal deposition? Yeah, sputtering. For example, you could add metal sputtering over here. In metal sputtering, you need a high vacuum. 10 to the power minus 8 torrs. Make a note, please. I expect you to know this. So, like I said, it's not a complete table, because I need you guys to get engaged. So, metal deposition is not included here, so I want you to include metal deposition. So typically the temperature goes up to 300 degrees Celsius. You could look it up in Malouf's book or outside. Pressure, extremely low. You know, to reach 10 to the power minus 9 volts, you need, torrs, you need 2 types of pumps. You need a rougher pump first, just to rough it up, bring it down to 10 to the power minus 3 torr. Then after that, you need this molecular pumps. Okay? So that brings you 10 to the power minus 9, but it's not going to happen in 1 hour. So it takes about overnight actually to reach 10 to the power minus 9. So if you want to do your metal deposition, you do a little prep the previous night, keep the pump on, then automatically takes over. You guys will see it in our facility. So after a while, then the molecular pump will take over. Okay? So this is a very important table to be completed. Okay? All right, let's look at a process. I'm talking about this device. Okay, so be patient with me. It's going to take about 10-15 minutes, hopefully. This is among the first MEMS devices. So it's called a resonator. Okay, a resonator means it's going to resonate. So you apply a little bit voltage, set it into motion, it keeps on resonating. Why do we care about resonators? If you want to measure actually vibration. So, no, if you want to sense mass, so it's vibrating, but you put a little bit of mass, then what happens? The frequency shifts. Then that frequency shift could be detected, so you could use that as mass sensing. But also, it's used as accelerometer. This is actually an accelerometer, but the difference between an accelerometer and a resonator is, in a resonator, the thing is always vibrating, continuously. It's functional only if it's vibrating. With accelerometer, it should not vibrate. Otherwise, your airbag is being deployed every second. So it's supposed to just hang out there, do nothing. But the moment something hits it, it's supposed to vibrate. Okay? But the same structure. Now, how do I turn this into a resonator? Just keep on applying the voltage difference between a plus and a minus. Then it will keep on vibrating. In terms of up to gigahertz, actually. Okay, some of the resonators are gigahertz. Now, the same thing could be used as a gyroscope. But for a gyro, you need what's called Coriolis effect. Have you guys heard of that? Look it up. Yeah, it's a very interesting effect, Coriolis effect. But I'm not going to cover that. That's 685. The only thing I want you to know is this basic design. That's the reason why I'm going to cover it right now. It could be used for 3 classes of structures. Just resonators, mass balancers, accelerometers, and gyros. Okay? Now, this is what really impresses me about this. So, Bill Tank, and I know this guy, he's now in a UC Irvine. So he used to be in Berkeley, he was a student. Now remember, this guy is an electrical engineer, okay? He never took mechanics of solids. He never took statics. Okay? So he did his circuits and all that kind of stuff. But look at the structure he came up with. So I mentioned this a little bit while ago. So remember, accelerometers and, well, particularly the context of accelerometer. What did we say? So an accelerometer only have, essentially what you have is you have a proof mass, something that has a mass. Then it's going to be supported from an anchor. Okay, so you're going to have 4 anchors. I don't even know what that is. So imagine if I have a proof mass like that, then I'm going to have an anchor, and the anchor is going to attach it to the substrate. Okay? So these are typically about 2-3 micron deep, but they support that. And then the proof mass is going to be attached to the anchor through beams, right? Because the stiffness is going to come from the beams. So if you make the beams very, very strong, I mean stiff, then you need a larger force to move the accelerometer. If you want to detect lower frequencies, then you make the beams compliant, less stiff, right? That's what you guys were supposed to cover in mechanics of solids and so on. Now imagine this guy. So this is his anchor, that's his proof mass, and he wanted low frequency. So if he connected his proof mass to the anchor through just one beam, and you could do the simulation, and then we're going to have some of you guys do a final design project on this, you'll find out that it's high frequency, that's gigahertz. So you need a huge pressure to vibrate this. For lower frequency, he came up with this folded beam design. That's when, when I give up, when mechanical engineers, and I give them some assignment looking at electrical engineering concept, okay, voltmeter, this, that, that. No, we've never thought. I've seen people having a really physical getting a headache just talking about electrical stuff. And I'm thinking, look at this guy. Never took statics, but he designed this structure which is highly compliant. Look at the way it's bending. So it's actually called outrigger, but it turns out even humans have discovered it. So if you look at the story how South Pacific Islands were discovered, so people actually built, if you look at their boats, they have these outrigger structures because they're very stable. So anybody who took mechanics of material will find it difficult, but trust me, if you use intuition, it makes sense to use this kind of structure. So I love that. So that's what I'm giving you as an example. This is the first resonator was done this low frequency. Now, how is this fabricated? Is what I would like to cover now. Okay, the next couple of slides. Okay, so polysilicon, we've talked about the material property. So I'm going to use polysilicon. Okay, mechanical property well over here I put 140 to 190, but you could assume it's 160 gigapascal as the average Young's modulus. Its yield is high. Steel has about 400 megapascal as yield, 300 to 400, but this could go up to a gigapascal. in terms of sigma y. Very flexible, no fatigue, remember SN curve. Now, this is the device I would like to build, micro machine. So, like I said, I have a proof mass. So, all this is the proof mass. These are my beams. Well, I mean, they're essentially a variation of this, but so you have a, in this particular case, they took the anchors out. So there's a lot of beautiful design over here. So here, the guy decided to put his anchor inside, but have outrigger beams. Over here, the guy decided to, or the person who designed it, decided to put the anchor outside. Proof mass is here, but you need two sets of electrodes, okay? One is the moving electrodes. So where we stopped, actually, essentially, I just said I want cross-section in the YY, and I mean, I gave you a little bit of background, but probably it's better if I finish the process, how this is done, okay? It's going to be very similar to what I'm going to cover. So that's going to be an overlap, but if you're already familiar with this, I think it's a good introduction. So, how did we end up with a structure like this? Okay? So, the first step is, now get into the MEMS mood, MEMS state of mind. So the first thing that you see, the gray layer, is your wafer, right? So if you could remind me a typical thickness of a wafer.
The 500 nanometers?
Right.
Or micro, sorry.
You answered the same way last time.
Same thing last time, yep.
Okay, how about the diameter? So the thickness is about half a millimeter, but how about the diameter? Anybody? 4 inches, which is, well, anything from 50, the smaller ones are 50 mm to 100 mm, which is 4 inches or 6 inches. So we start with this wafer, and so these are color coded. So what you see as, you know, kind of light orange shows you, or the blue one is, you know, for example, this layer, okay? So what I do is first I do end plus diffusion, okay, with phosphorus diffusion. And the reason is most of the stuff that we make are electrostatic devices, so they store a lot of charge. And you don't want those charges, if they are excess, you don't want those charges to go through the wafer, actually. So what you do is you put excess of charge already. Okay, that's the way, it's just like the way we fight with fire sometimes, right? So you do this, set fire ahead of it and then remove the material. So essentially you diffuse with N+, so you have excess of electrons, so you're not going to push additional electrons. Then we do 0.5 micron thermal oxide. The process will be, you could remind me? Oxidation, right? Oxidation process, temperature? Yeah, about 1080 degrees, and then you put oxygen, right? Okay, so I grow 0.5 micron thermal oxide, that's for insulation. Then on top of that, I do additional insulation layer. What's the other insulation in addition to oxide? Anybody remember? Nitride? Nitride, yeah. So we deposit 0.15 micron, 150 nanometers of nitride using LPCVD. What LPCVD stands for? Low pressure chemical vapor deposition. Okay. All right. So at this point, I have my wafer, I have a thermal oxide, and I have a nitride. So both of them are insulation. Okay. Then on top of that, what I'm going to do is I'm going to deposit 0.3 micron, very thin, 0.3 micron, because I'm going to go deeper later on. So I deposit the first poly layer, polysilicon. Okay. So I deposit my polysilicon. That's the meal kind of color, right? Using LPCVD. So the next thing is, once I deposit, then I need to open it up. So what do I do? Right? Nothing. Okay.
To undercut?
No, well, first I deposit, right? But the next thing is, usually after you deposit, you want to extract, right? So we call that patterning.
Patterning,
Yeah. With lithography. Yeah. So you do the first lithography. So we're going to do a lot of this again and again today. Okay, I'm going to work out for a given device. I mean, what we have seen is a real direct device, but I'm going to work through all the process. And then what? I do it. Then I do a patterning with a photolithography. Okay. So what you see over here is actually a pattern. So to do a patterning, you have to deposit the photoresist. Then you bring the mask. And then you cover everything else except this guy. And then you come with a DRI or a wet etching and then etch that. And then eventually strip off the photoresist. So yeah, positive for example. So at the end, you have poly 0, which is pattern. Okay? So there's a whole process. When I say one detail, that's a whole series of processes. Deposit the photoresist, expose it, do your etching, and then strip it. So the whole thing is called lethal, as you remember. Okay, once I have done this, right now I have only one poly layer, okay, and 2 insulation layers. So the next one is interesting layer, light blue. 2 microns of PSG, phosphosilicate glass. I need you to remember this element, this material. It's a sacrificial material. If I ask you, okay, give me an example of a sacrificial material, you should be able to say PSG. Okay? It's going to be etched away very easily with hydrochloric acid or sulfuric acid or any of the acids. Okay? So what you do is, what we do is we deposit this 2 micron, very thick. So far what you have seen is 0.15 micron, 0.2 micron, very small. But now, being brave, 2 microns of PSG. Now remember, this is a sacrificial layer, which means eventually I'm going to get rid of it. So it's going to give me a gap of 2 microns for my moving parts. And that's why I'm going deep. Okay. Now, the first thing I want you to notice is, remember there was a hole here, you patterned. So when I do the cartoon, when it fills it up, it's not going to fill it up in such a way that it's going to remain plain, straight line. Because what's going to happen is, imagine you're putting a general in a kind of a hole. What happens is it's going to fill it, and it's going to assume this kind of shape. Okay? That's why when you do homework number 2, you get shapes like that. They occur because of this. Okay? All right. So we have done our PSG, sacrificial layer. And what I'm going to do is I'm going to create that magical structure for dimple. Now, with dimple, I'm not going to go through the whole thing. All I need is just a copy of this, okay? So I have 2 microns, and the dimple is not going to touch all the way in because it's going to get structured, otherwise it's going to get stuck. I need space, but I need that springing action from the dimple. So what I do is I do one more lithography on the PSG. So when we say lithography, it means now I'm going to deposit a positive photoresist. I'm going to expose it with a mask, and that mask is called dimple mask. So it only has this feature around here. So, actually I'm doing 2 things. The first one is I create a dimple. So I do the first photo mask, expose, and then etch the spot, and then, do not remove the photoresist yet. Then I do additional lethal, because I'm going to create what's called an anchor. Eventually, so this is the part that's going on down to 3 meters, right? But you also need something to be anchored, because I'm going to put additional layers, right? So in preparation for that, what I'm going to do is I'm going to create this etching, so-called anchor etching. Typical etching, reactive ion etching, which is, what kind of etching is that? Dry, wet? Dry, it's DRIE. Typically with hydrofluoric gas, which is an acid. Okay, any questions so far? So we're building the structure layer by layer. So what do you think is going to follow now? A question? Yeah.
Yeah. So between like the etching to create those dimples, like which on the right side, and then create the anchor, those are 2 different etching processes.
Yes.
So one's like the time etching it over reactive.
Yeah, both of them are time, but so what you do is, so I skip 2 things here, right? So the first one I cover this guy. I'm going to have a photoresist everywhere. And then I'm going to get a mask and then just expose only these 2 parts, do my thing, then strip the whole thing out. Because when you're digging, so this is about 600, I think 0.6 micron. So remember, the whole thing is 2 micron. So dimples are typically about 0.6 micron. So by that time, already the photoresist is weak. Remember, everything will etch. It's just the rating, or the etching rating was better. Some of them would etch 5 micron per 10 minutes. Some of them 10 microns. So anyway, so once I get rid of that, strip that one out, then you do additional.
Okay.
Well,
So it looks like in that single photolithography process, you do the dimple and the anchor?
no, dimple first, then anchor.
Oh, two separate.
I'll just keep my wafer out.
Okay. So I was wondering how you got one deeper than the other.
Yeah, so it's essentially two.
Okay.
And then we're going to do this again with the 4-bar polymers process, right? But I just want to give you a brief introduction right now. So, everybody with me on this? Yes?
Why would we have to have so many layers of insulation? What does that serve as?
What insulation? Strong insulation. So the first series of, so first let me answer the why we put N class. Okay. So the first accelerometers, people were using them, and then essentially what you're doing is actually you're pulsing these things billions of times, and it turns out over a period of time charges build up. And the charges are passing through the wafer and then going to the electronics. You know, people worry about that. Okay, how do you prevent that? Just put a guard, kind of seal. And then what you're going to seal is just bombard it with additional high concentration N plus. So that worked. But then again, the insulation was not adequate, 0.5 micron. So we say, okay, let's do a low stress nitride. So these are mainly out of practice. There is no theory. The theoretical basis is okay. I could do 1 micron of silicon dioxide, or 1 micron of nitride. But typically works better, half a micron oxide, another nitride there. Okay, good questions. Now, once I have this, what do you think is the next layer? So remember, this is just a sacrificial layer. So after sacrificial layer comes some structural layer, right? I have to have something that's going to float. If you've already done your homework, then you already know what's going to come. So this guy, I call it poly 0, the orange one. Now another poly layer is coming, and I'm going to call that poly 1. Okay? And you're going to see that. All right, the green one. 2 microns thick. It's thick. It's very, very thick. In fact, these are some of the examples. So there is a poly 0 layer at the bottom. Now, these guys, the real structures, are poly 1. 2 micron. And the sacrificial layer was actually going to be helpful for this guy. Because what I want to move is the poly 1 layer. Okay? So when you deposit, again, look at the way it's going to deposit. The jello example. Right? So there was that dimple. So it comes in, it fills it. When it fills it over here, it's going to produce the same dimple function. Okay? And the same thing here. And then the anchor over there. So I have 2 dimples. 1 dimple here, another dimple here. And the other, this guy is, of course, the anchor. It went all the way. Therefore, that's why you see deeper here and then deeper over there. Now, as you can see over here, I've skipped one step, which is first I deposit, then there's going to be lithography, right? Again, I'm going to cover this in detail in a formal way, but that shows you. Okay, I thought I saw somebody asking a question. Yes?
So why would it have a dimple and not straight?
Here?
Yeah. Why does it here?
So I have an experiment for you. When you go home, go to grocery, buy a gel, and try to deposit it with some container with a hole. So the way it does, any viscous material, when it flows, it's going to flow like this. So it's going to fill it up. So as you deposit it, remember, the deposition rate is the same. So something comes in, first it has to fill in this guy. So as you keep on increasing, then what's happening is this guy has to catch up.
Does it harden quickly?
Oh yeah. I mean, this will happen within minutes actually. So your spot. So remember, LPCVD, chemical vapor deposition, right? Comes like this, I told you, and then fills the hole within minutes. As soon as you remember the temperature, it's going to start. Okay, but the way it's going to fill it in is not going to be a straight line. I mean, this is a mechanics problem. Okay. All right, so we have this. Then the next thing I want to do is, I'm going to do a very weird thing. So I want you to pay attention. Well, just give me a second. Let me make this one. So I want you to pay attention to this. So far, I've been talking about the word mask. And mask was that transparency of the glass stuff, which I use, which has a feature, right? But I also use the same word in a different context. I don't know if you remember that. So mask, actually, it masks it from being exposed. So I could use, in addition to that transparency, which is a mask, with a pattern, I could also use layers like the photoresist that I'm doing is actually it's masking it from being attacked. Remember, that's the whole idea. Now, I got this guy, 2 micron deep, something that you haven't seen so far. So typically we've been playing with 0.15 micron, 0.2 micron. Then I have this 2 micron guy and I want to pattern it. If I use a photoresist, remember everything etches, it's just a rate. Now if I use a photoresist and I keep it for about half an hour, before I reach here, the 2 micron, the photoresist will be stripped out. It will be etched that way. So I have to use another kind of material to mask things. So this time PSG, the same sacrificial layer, turns out could be used as a mask. So very thin because it's a metal oxide. So PSG is phosphosilicate glass. So I should write it. Because something that I expect you to know. So let me write it down. Oh, I thought I had. Yeah. Okay, so. PSG phosphosilicate glass. Okay, so I deposit the phosphosilicate glass. Again, the same pattern. Whenever you have a dimple, it's going to go like this and all that kind of stuff. Okay. Then what do? I'm sorry, pattern, right? Will, you had a question. Sorry.
Yeah. Do you have to go through a bonding process to get the anchor to stick to the nitrate, or is
it does. It sticks very well.
Just sticks well.
Yeah. Now, when it's metal, it's a different story. We're going to come back to that. So gold doesn't stick very well. So I have to use what's called a needle layer. Yes.
Not to make you repeat yourself, but the PSG that you put on top of the
Polygon. Yeah.
You do that because it's going to act like photoresist that just doesn't etch as fast.
That's right. It's harder. It's a glass as opposed to. So when you come to my lab, you're going to see photoresist, and you're going to be surprised. So this is what's preventing actually silicon from being etched. It looks like tea or coffee. It's very thin, non-viscous material. But polymers are beautiful because they don't get attacked by acids. Or they get attacked but slowly, as compared to silicon and metal and so on. Okay? So the problem is, I can't use a tea or coffee looking material to go 2 microns. So I use this thicker solid material with the glass. Okay, so far so good. Now, using that mask, now here's where it gets complicated, okay? Hopefully you stay with me. So I put the phosphosilicate glass, this guy, right? Now I'm trying to etch through this, which means I have to first make openings through PSG. Look how really messed up it gets. Okay, then how do I do that? So I have to go back to Shipley, which I was by mouthing 3 minutes ago. Okay, so you go back to Shipley and you make opening through the real mask. Does that make sense? I know it's confusing. But we're going to cover it again with the larger polymers process. But I mean, think of it this way. So I'm going to use this glass, a thicker material as a mask material. But to be a mask, of course, it has to mask not everything, but only selected areas. So if that's going to be the aim, then I have to have some of the areas at least darked out, removed. And how am I going to remove them? Back to the old school, Shipley. So we're going to do a photolithography. So I have a mask, which is just called PSG mask. You bring it over here, then you make openings. Now, if you remember, I want you to think about homework number 2. Those of you have already done. Remember the section that we did. So you know that over here I'm going to have an opening, because that's the anchor of my accelerometer. So these are the fingers, right? The moving fingers, and then, well, yeah, depending on the section that you did. So the anchor, the moving fingers, then there's going to be a proof mass, but there is going to be an interruption here, right? Okay. Now, what's going to happen is, as I promised, this part is going to be cut. So I had my PSG, I did a lithography on the PSG, I made opening over there, went in and then etched away the poly 0. Still I had the PSG left. Then once that was completed, then I go and remove the PSG. Then you have this beautiful structure at this point. Does that make sense? Okay, it will make sense slowly, okay? All right, now at this point, so what I have is, I'm not interested on the metal for now. No, I want to simplify your life. So at this point, I'm almost done. I'm actually done. So what I do is, I will remove the first PSG layer, the 2 micron teeth. For this purpose, because like the shot there, I don't need it anymore. Go in, etch it away. It's gone. And what you will have is these guys actually suspended. So this green guy is, well, it's like white, snowy mass kind of stuff. And this, folks, is what you have in the homework number 2. Make sense? Okay, any